have before us a states data set that I've created for some of these SPSS tutorials, and what we're going to do here is demonstrate how to generate regression analysis results as well as construct confidence intervals in SPSS. What will come up here first of all to generate a regression model, let's go to Analyze, and I'll come down to Regression, and I'm going to come over and I will just choose Linear for the option. You notice there are various different kinds of regression. We're just going to be using OLS, or ordinary least squares regression, which is a linear regression model. Click to open that up. Now what we have before us now is the list of variables in our data set, as well as a box for a dependent variable. Let's go ahead and click Young Mom. That's going to be our dependent variable. It's birth to women under 20 years of age for the 50 states in the District of Columbia. There are 51 cases here for 1 year. And now what we're going to do is select our independent variables. I'm going to first of all select Education 12, and we'll just leave it at this for a bivariate regression model. Now I'm going to go ahead and not worry about any of the statistics or the plots or options here. There's a lot you can do with SPSS regression routine. I'm just going to show the basic OLS regression model. So I'll click OK, and we'll look at the output. Now you notice the very first box that it showed here displays the dependent variable and also then the independent variable that is entered within the data within the regression model. Now what it does is SPSS always reports the displays the variable labels for your variables, not the variable names. As we go down to the model summary, this reports goodness of fit, and what we would be interested in here is the R-square value of 0.616. So knowing the percent of individuals in a state who are 25 years and older who have at least 12 years of education or high school degree explains about 62% of the variation we see in the percent of births to young mothers. A fairly large amount of variation. As we come down here, we see the analysis of variance table, and the analysis of variance table here can be useful for testing whether or not the R-square value is statistically different from 0. In essence, if we were testing the R-square value and its significance, we would be reporting the F-test, which has a value of 78.446. It has a significance value, that's our probability value, of 0.000. Now it looks like it's 0, that there's no chance that this data came from a population described by the null hypothesis, and the null hypothesis would be then that the population parameter for the R-square, which is called rho, that rho is equal to 0. Looks like it has no chance. But what we do here is we see then that SPSS only reports the 3 first decimals, so out to the thousandths place. If we double click on the output, it now opens it up and we can actually edit, but I'm not going to worry about editing it here. If I move my cursor right over top of the significance value, that particular cell, you notice it is 9.6414 e to the minus 12. So if we put 11 zeros in front of the 9 there and then a decimal point to the left of that, that would be the probability value. So it's very unlikely then that this sample that generated this particular R-square of 0.616 came from a population described by the null hypothesis of 0. How I would report this is I would indicate the probability value is less than 0.001 and not reported as 0. As we scroll down here, we now see the output for the regression coefficient. We see the unstandardized B, that's the regression coefficient. The constant is the intercept of 37.005. We see its standard error. Also, we notice then for the independent variable, a percent of population with 12 plus years of education has a value of minus 0.357. So if I were writing out the regression line as an equation, I would write it as y equals 37.005 minus 0.357x, and that's our regression model. You notice the standard error is 0.04 for the regression coefficient. We can generate a t-test for a test of statistical significance for that regression coefficient by taking the unstandardized coefficient of minus 0.357, divide it by 0.04, and then we end up with a t-test value of minus 8.857. Now its significance value also is reported here as 0, but it's not exactly 0. It's going to be a very small value. So I'll click on the output if I want to know the exact value of the probability value of this particular t-test. And once I click on it to activate it, actually double click on it to activate it. Now I can edit it, but all I want to do is move my cursor on top of the significance value to see what the actual probability value is. 3.6055 e to the minus 18. So it's highly unlikely that this sample was drawn from a population where the regression coefficient is actually a value of 0 for this variable. So in that case, what I would do is I report this probability value as being less than 0.001. Don't report it as 0, report it as less than 0.001. So it's significant at even the 99.9% confidence level. The next thing I'll do is generate another regression model, but this time we'll have more than one regression coefficient reported, so more than one independent variable. Come back to Analyze, and I'll come down again to Regression, and I'll come over and choose the linear option. Now here I'll still keep Education 12, but let's say what I wanted to also add in there is the percent of individuals who live below the poverty level, or the poor PCT, poor percent. The unemployment rate, this is percent of individuals who are unemployed. And let's say I also wanted to include the urban 86. This is the percent of individuals in a state who live in metropolitan areas, is what the variable is. Now you notice as I enter in the variables, it just puts them in the order which I enter them. If I wanted to display the variables in a different order, the coefficients in a different order, I can go back and change that order that I have here by just bringing them in one at a time in a different order. But we scroll down, we can see all the variables we have here in our model. I'll click OK, and again you notice here that the first output indicates the dependent variable for the model in footnote A to this very first table of output, and you notice then that the variable labels for all the independent variables are listed in this first cell here. Now it's a little hard to read, but they actually do have commas separating the variable labels for each of the independent variables, but it lists the independent variables then we see for the regression model. Scroll down a little bit, we see the model summary, that's goodness of fit. We notice 0.818 is the R-square value, so the regression model explains about 82% of the variation in percent of births to young women. So what we see here is a greater goodness of fit. Adding the additional variables does help to explain more variation among the states in percent of births to young mothers. You also have seen here an adjusted R-square, which was reported before. When we have an adjusted R-square, this is typically what we'll report when we have multiple models but with different numbers of independent variables. We can't interpret the adjusted R-square as percent of variation explained. With R-square, it's about 82% of the variation. The dependent variable is explained by the model. We can't say that with adjusted R-square. Instead, what we merely would do is if we have different models with different numbers of independent variables but the same dependent variable, we would just then report the adjusted R-square and indicate which of the models had the higher adjusted R-square, may have the higher goodness of fit. We also notice down here then the ANOVA table, which provides the mean square regression and mean square residual, its F-test and its significance value, as I mentioned before. And then we see the list of independent variables and their coefficients. So the regression model would be y equals 16.467 minus 0.191x1 plus 0.429 times x2 plus 0.378 times x3 plus 0.02 x4. That would be the regression model. For each of these independent variables, you notice then we have um, a standard error, and we can compute then a t-test for the test of the significance of these variables by taking the unstandardized coefficient of minus 0.191 for the first variable, educational attainment, divided by 0.042, and we end up then with the t-test of minus 0.4509. Its significance value is listed here as 0.00. I'll just double click once to on the output, and it opens up the formatting or the editor here for the output. I move my cursor right over top of the probability value. Its probability value is 0.000045. So it's still a fairly low probability value. So it's highly unlikely that this sample was drawn from a population where education and births to young mothers is not related, that its coefficient is 0. No, its coefficient is different than 0. But these probability values are two-tailed probability values. If I were conducting a one-tailed test for any of these coefficients, I would just take the probability value and divide by 2, and that would be the probability value then for that t-test for a one-tailed test. We also notice here as we go down that the persons below poverty level, that also is statistically significant. I will move the cursor over top of it. It's 0.000143. Again, if you double click on the output so that you can edit it, you can now move the cursor over top of the cell that has the significance value and see a more detailed output. So I would indicate then that both of these first two variables have t-tests that are statistically significant at the 99.9% confidence level, or the probability values are less than 0.001. We notice the unemployment rate is also statistically significant at the 95 or 99% confidence levels. But if we wanted to use a 99% confidence level, then we notice that this significance value would no longer be, that this t-test would no longer be statistically significant. But its probability value is 0.002. In metropolitan population, percent of population lives in metropolitan areas, this variable is not statistically significant at the 95% confidence level. So we notice here its t-test of 1.92 has a probability value of 0.061. So if we were using a 95% confidence level for our standard for statistical significance, this would not be statistically significant. If we were using, however, a 90% confidence level, then it would be statistically significant because the probability value would be less than the alpha of 0.10. So whether or not metropolitan population is variable significant, I should say its t-test is statistically significant, is a function of what our confidence level we use for generating then, or for determining statistical significance. And that's how you go about then generating a regression model in SPSS and interpreting the output that you're given. One last thing I'd like to just point out in terms of the SPSS output for the regression routine is the column that's labeled standardized coefficients, or beta. If you would happen to generate a standardized regression model, and what a standardized regression model is nothing more than taking the dependent variable and all the independent variables and transforming them into z-scores. Then what we would do is just report the standardized regression coefficients, what are oftentimes called beta coefficients. Now you notice there is no coefficient reported for the constant, for the intercept. That's because once we transform all of our variables into z-scores, then the intercept for that model would automatically be 0 by definition mathematically. I should say mathematically would be 0. And in that case, there is no intercept that's reported. So if we were interested in reporting the results of a standardized regression coefficient, we report then these coefficients that are listed under the beta column. But also the t-test and probability values are accurate or appropriate also for the standardized coefficients as well. So in the case you had to report a standardized regression model, that's where you find the output here for SPSS. In addition to reporting the regression coefficients as well as t-tests and the probability values of t-tests, we can also generate confidence intervals for these regression coefficients. What we'll do is come back up to Analyze menu, left mouse button to open that up, come back down to Regression, and come over to choose the linear option. And you notice that what still is within the dependent and independent variable boxes is the exact same information we had before, the same variables, which we'll use that again. What will come up now is we'll click on the button Statistics we see here. And the first thing that we'll notice here is a confidence interval that's listed right underneath the regression coefficients. I'll go ahead and check that box. And now you notice we see the 95% confidence level is the default. We'll go ahead and accept that. Click Continue. And then now let's run our regression model. Notice the output will be the same until we get down to the regression coefficients themselves. And now what we see here, the two columns to the far right of the coefficients box, that output is the confidence interval. So the confidence interval for education with 12 plus years, a population with 12 plus years of education, or the educational attainment variable, would have the lower limit of minus 0.276 and the upper limit of minus 0.106. So if we notice for each of these confidence intervals, 0 is contained not in the first confidence interval, nor the second for poverty rate, nor for unemployment rate, but 0 would be contained within the confidence interval for metropolitan population, the urban population. And that implies then at the 95% confidence level, it's likely then that this sample came from a population where the relationship between these two variables, the metropolitan population and the births to young women, could very well be 0, so not a statistically significant relationship. So the same decisions can be made about whether we have a significant relationship by reporting confidence intervals or by reporting our regression coefficients along with their t-values and probability values. But if we're generating and reporting confidence intervals, we would only report the confidence intervals, not the other information that we see here. But let's say I wanted to use a different standard for statistical significance. I'll come back up to Analyze, come back down to Regression, come over to Linear. Let's say I wanted to change to a 99% confidence level. Click on Statistics. Just highlight that box where 95 is located. Let's say I wanted to make it the 99% confidence level. Click Continue. Now click OK. And we'll notice the exact same output, except now we see that the 99% confidence interval is reported. So those will be different lower and upper limits because now we will have a wider confidence interval. But again, we make the same conclusion. 0 is not contained in the intervals for the first 3 variables, and we tend not to report the confidence interval for the constant or the intercept. So looking at the first 3 variables, population with 12 plus years education, persons below poverty level, and the unemployment rate, 0 is not contained in any of those intervals. So in that case, the relationship between those 3 variables and the dependent variable would all be statistically significant at the 99% confidence level, but 0 is contained within the confidence level for the 99% level for metropolitan population, so that would not be statistically different from 0. But let's say I wanted to generate instead a confidence interval for the 90% level. Come to Linear, come back to Statistics, and I would now report. Type in 90, click Continue, click OK, and as long as the probability value is less than 0.1, we will see that 0 will not be contained within that confidence interval. So as we go from 99 to 95 to 90% confidence intervals, levels rather, we see the intervals will get smaller and smaller. And now we notice that for the metropolitan population variable, 0 is not contained in that interval between the lower limit of 0.003 and the upper limit 0.037, so it would be statistically significant or different from 0 at the 90% confidence level. But I typically would resist using a 90% confidence level. There's some cases where it's appropriate. We can debate whether or not it's appropriate in this context. But in any event, what we see here is we can generate regression output as well as including in that output information for confidence intervals, and we can change the option as to what confidence level we want to generate the confidence intervals for.